Welcome to Finite Element Lectures by Civil Thinking, and this is our another class in Finite Element Method Analysis. Now, before I move on, I suggest you to please watch the video lectures on Finite Element Method one by one as in the playlist so that you understand better. The playlist link is in the description, or also you can click on the pop-up on your screen. Now, coming to the today's class, in this class we will be talking about finding the stiffness matrix, okay, deriving the stiffness matrix based on direct method, okay. However, there are multiple methods to find the stiffness matrix, and when appropriate we will be talking about variational method and weighted residual method too, okay. But right now in this class we will be talking about direct method, okay. And in this class we will talk about the stiffness matrix, okay, of what rod elements or 1D elements, okay. Now I have already told you what are 1D elements, like line elements, the rods and beams and everything. You can watch a video lecture on the types of elements. I have already made a video lecture, okay. So right now we'll be talking about 1D elements, okay. So let us consider a rod, okay. Let us say this is fixed here and you are applying a force F at this point, okay. Now because of this F force, this beam will it will deform and it will elongate, right? Let us say for example the deflection is U, okay. Now we can apply, from the Hooke's law we can say stress is E times of strain, okay. Now let us assume this has a cross section, okay. This has a cross section, its area is L, okay, and the length of this bar is L initially, okay. So the stress is Young's modulus times strain. Now we can, the direct stress, it is sigma. We know the stress is what? Force divided by cross section area, okay. So force is F and cross section area is A, so we can write here as F divided by A, it is equal E, I will keep as it is, times strain. Now strain is what? It is change in length, right? Delta L divided by original length, right? Now the change in length is U, right? This is the deformation, okay. So it is U divided by L, okay. So I can write here U divided by L, okay. Now I can further rearrange this equation. What I will get? I will get force is equal, I will shift this A to the right side, so it is going to be E times U by L times A, okay. Now further if I rearrange this, it is going to be like EA divided by L times U, okay. I have rearranged this, so we got this equation. Right now remember we have talked about the the stiffness equation, right? Earlier we said force is equal to kx, right? This is the stiffness equation in if we put it in matrices, it is going to be a stiffness equation, right? Now from here if we compare it with this equation, F equal to ku, because x is when I write force is kx, x is displacement, okay. But right now I have assumed displacement to be u, okay. So I place u instead of x. So from when I compare these two equations, so this is F, both are F, and here both are u, and here it is k and here it is EA by L, okay. Now from here, right, what we get k is equal to EA divided by L, okay. So we got the stiffness equation, okay, but we have not done meshing yet, right? So as I've told you before, when we do the meshing, okay, because meshing creates divides a body into multiple elements, okay, then we don't talk about K, we talk about K matrix, right? Stiffness matrix, okay. Similarly, we don't talk about force when we mesh a body, we talk about force or load matrix, right? Then we don't just talk about X, we talk about what? We talk about displacement matrix after meshing, right? After meshing, okay, it is going to be F is equal kx, okay. So now right now k is equal to EA by L. It is for, you know, for the whole body, right, without meshing, right. This is in fact not the part of FEM, right, because FEM deals with the meshed body. So when we do the meshing, this k is going to be like this, okay, it is going to be something like this, and there will be some another matrix, okay. So after meshing, okay, after meshing we will get something, okay, and in this video lecture we will see what we get here, okay. So let us do the meshing, okay. So if I have this body, okay, now you know what I will do, because in meshing we usually what we, you know, mesh into many elements, right, but we are not going to do that right now, okay, because I want to keep, you know, because this is an introductory video, I will keep a single element, okay. So I have, this is our, you know, rod, okay, so I will convert it into only a single element, okay. So this is node 1 and this is node 2, okay. So we have only one element, okay. Now when we talk about direct method, there are some steps, okay. There are some steps. With the help of, you know, those steps we can, you know, formulate the stiffness matrix, okay. Basically we will get this thing, okay. So what are the steps? Now let us say, you know, for an we have total, you know, total n degrees of freedom, okay. Then there will be steps. Then step 1 is what, set first degree of freedom free, okay, not equal to 0, and all other degree of freedom equal to 0, okay. So we have to, you know, we have to fix, like we have to fix one node. If we talk about step 1, so this is node 1, we will keep it free and, you know, fix all other, okay. When we fix something, the degree of freedom gets 0, and that's why I write degree of freedom is equal to 0. It means what, I have set them as fixed, okay. So when it is not equal to 0, so it is free, okay. This means free, okay. And when we do this, we will get one equation, okay. For example, equation number 1, okay. Then step 2 is going to be set, you know, second degree of freedom free, right, that means not equal to 0, and all other degrees of freedom equal to 0, okay. This will give you equation 2, okay. So you have to follow all these steps, okay, up to what, because we have n degrees of freedom, so we will get up to step n, okay. Here we will set what, nth degree of freedom free, not 0, and all other equal to 0, okay. So this will give us nth equation, okay. Then because we have n degrees of freedom, we have to follow n plus 1 steps, okay. So step n plus 1 is going to be what, it is going to be, we have to, you know, combine all steps, okay, from 1 to n, okay. So when you combine all the steps, okay, now this will give you the stiffness matrix, okay. This will give you the value of stiffness matrix as what, EA by L, right, and there will be something here, okay. So we will see this something, okay. So let me take, you know, an actual problem, actual example here. For example, let us take, you know, let us take a bar, okay. For simplicity, I will convert it only one element. Okay, so for example, this is node I, this is node J. Okay, so this element is between I and J node. Okay, so what we are going to do, so our first step is going to be what? So I will write here step 1. What was step 1? Keep ith node free, right? And because there is only I and J nodes, so I will keep J fixed. Okay, because we have to keep one node free and all other fixed. Okay, so it is going to be something like this. Okay, if I draw it here, okay, so I will keep this free, okay, and I will keep this fixed, right? This is I, this is J node, right? So I will apply a force here. Okay, let us say this is Fi. Okay, why Fi? Because it is acting at node I. Okay, so because of Fi, it is going to, you know, compress, right? So it is going to be something like this. Okay, let us say the deformation here is U I. Okay, so from here, because we know what was the equation? The equation was what? F is equal to EA by L, right? F is equal to EA by L, right? Force is equal to EA divided by L times U. Okay, times U. Okay, so from here, if we put the value of F instead of Fi, okay, we substitute Fi into F, so we will get Fi is equal to what? E A by L times U. Instead of U, we will write Ui. Okay, because we will apply this equation to each node. Okay, so first is I node. Okay, for the I node, it is going to be Ei. Okay, now let us apply this equation on node J. Okay, now remember this, you know, let us say this is x-axis, okay, this is y-axis. Okay, now our, you know, our rod, our 1D bar, our 1D rod is along x-axis, right? So if I want to draw the free body diagram here, okay, so it is going to be, there is going to be a force like this, reaction force, right? It is going to be Fj, right? So Fj is going to be equal to Fi, right, but in opposite direction. Okay, so it is minus Fi. Okay, so I can write the value of Fj here. Fj is, because Fj is what? Negative of Fi, right? So it is minus E upon L into Ui. Okay, so this was step 1. Okay, so now we will see step 2. Okay, so step 2 is what? I will keep J as free, okay, and I as fixed. Okay, because we have to keep one free and all other fixed, because there is only, when it comes to J, after J there is only one, that is I. Okay, so it is going to be something like this, right? This is I, this is J, so I have to set the J as free and I have to keep this as I have to keep it as fixed. Okay, now let us say there is a force here at J and it is equal to Fj. Okay, now for Fj we will write Ea by L, right? Ea by L times U. Now because, you know, Fj, there will be, the J will displace, right? Let us say Uj is the displacement of J. Okay, so it is going to be Uj. Now when we talk about I, there will be a reaction, right? Because this is a fixed support, there is going to be a reaction and it is going to be equal but opposed to Fj, right? So it is going to be Fi. So Fi is going to be what? Fi is going to be negative of Fj, right? Negative Y, because it's in the opposite direction, but the magnitude is going to be same. Okay, so for Fi, I can write here Fi is what? minus of Fj, right? So minus of EA by L times Uj. Okay, so we had what was the total degree of freedom here? It was, you know, like this is node 1, this is node 1, this is node 2. Okay, now in a bar, in a rod, in a 1D element, there is only one possibility of motion, right? Because when we apply a force, the, you know, the node can move in only in the direction of force. Okay, so there is only 1 degree of freedom at one node. Okay, so there are 2 nodes, so what will be the total degree of freedom? 1 plus 1, right? This is, there are 2 nodes, right? Total nodes times degree of freedom of each node. Okay, so total nodes are 2, right? It is going to be 2, and degree of freedom of each node is 1. Why only 1? Because in 1D it can only move in along one axis, right? So 2 times 1, it is 2. Okay, so how many steps we will take? It was 2, because I have told you, if there is where is it? Yes, if there is n degrees of freedom, right? So we will apply how many steps? N plus 1. Okay, so if degree of freedom is 2, okay, so how many steps is going to be? 2 plus 1, right? So 3 steps in 2 degrees of freedom. Okay, so we have followed 2 steps. Okay, so step 3 is going to be what? We have to combine all. Okay, this is the n plus 1 step, right? This is the n plus 1 step. Okay, we have to combine all the steps from 1 to n. Okay, so 2 steps we will combine. Okay, combine step 1 and step 2, right? Step 1 and step 2. What does it mean to combine? We basically mean we will, you know, find all the forces. Okay, Fi, for example, Fi and Fj. Here it is Fi. Okay, I will copy it here. Okay, we have copied this, then we have Fj here. Okay, this is Fj. Okay, then from here we will also copy Fi, and this is our Fj. Okay, this is our Fj, right? So right now we can see what this is the value of Fi, but this is also the value of Fi. This is the value of Fj, but this is also the value of Fj. Remember, I have told you what I have told you, when we do the meshing, we don't talk about F equal to Kx. Okay, because after meshing, what is going to happen? After meshing, we will get elements, right? Elements and nodes. So it is going to be F matrix, okay, is equal to stiffness matrix times X matrix. And this is, we will understand, because we got multiple values of F. Okay, so if it was single F, what we would do? We couldn't do anything, right? Now we have multiple values, so the one of the ways is, to cover up everything, because here we had only one element, right, and 2 nodes. But what is going to happen when there are multiple elements and multiple nodes? So better is to keep them in matrix so that we don't miss any information. Okay, so when we put it in the matrix form, we can keep it like this. Okay, this is going to be F equal to Kx, right? This is our basic matrix, right? Now I will combine all of them. So from here, from these two, I will get the value of Fi to be what? Fi is going to be Ea by L times Ui, and what? Minus Ea by L uj, right? So from here fi is going to be what? ea by l. I will put ea by l common. It is going to be ui minus uj, right? So this is our fi, and from these two I will get the value of fj, right? So fj is going to be, again here is ea by l, here is ea by l. I will keep them as common, l, then it is minus ui and plus uj, right? Plus uj, okay? So now we can combine these two, okay? We can combine these two in matrix, okay? So fi and fj, I will keep them in one matrix, okay? And this ea by l, ea by l, I will put them outside, okay? And ui minus uj minus uj, ui plus uj, I will keep them in matrix, okay? ui minus uj minus ui plus uj, right? Now when we simplify this here, it is going to be fi fj, it is going to be ea by l times, now see this is, you know, ui uj ui uj. So ui and uj, these are only two variables here, okay? So I can put them here, ui and uj. When we, you know, remove the ui and uj, here is going to be 1 minus 1 minus 1 and 1, right? Because I kept ui and uj outside, right? Then here it is going to be the coefficients, right? 1 negative 1 negative 1, because here it is negative ui, because I kept the ui outside. So here will be what will be left? Minus 1, right? Similarly here I will keep the ui outside here as it is ui, so here will be 1, right? So it is going to be 1 minus 1 minus 1 1, okay? Minus 1 and 1, okay? So this is what? F is equal to k times u, okay? So from here, what is the value of k? K is this, okay? So from here I will write k is what? ea by l times 1 minus 1 minus 1 and 1, okay? So this is our what? This is our matrix, okay? Stiffness matrix for, okay, for our rod element or 1D element, okay? 1D element with axial forces, right? Because rod or bar, they carry axial forces, okay? Now this is also applicable, okay, to other things too. We will talk about those in the coming lectures, okay? Now right now let's talk about the order of the matrices in this. Now if you look at this, how many rows are here? 1 and 2. How many columns are here? 1 and 2. So order of a matrix is what? Row times columns, right? So it is 1 and 2 rows, 2 cross how many columns? 1 and 2. Row, number of rows multiplied by number of columns. So we got 2 cross 2, okay? Now again if I talk about this, now this is 2 cross 2, right? Now here in this is what? This is our displacement matrix ui and uj. How many rows are here? 1 and 2. 2 cross how many columns? Only 1, right? 2 cross 1. Now this load matrix, how many rows are here? 1 and 2 cross how many columns? Only 1, okay? Now if you see what was our degree of freedom? Our degree of freedom was what? 2, right? This was our degree of freedom, okay? Total degree of freedom. So it is 2, and you can see here we got also 2 here, okay? 2 cross 2 and 2, okay? So from here we conclude what? The order of the load matrix, okay? F equal to 2 times 1, okay? The order is what? Total degree of freedom times 1, okay? So I can write here, okay? So order of the force matrix is total degree of freedom times 1 is equal to, then we have stiffness equation. Okay, by the way, this is called stiffness coefficient equations, okay, because we keep ui and ug outside, so this is stiffness coefficients. Okay, so what was the order here? 2 cross 2, and 2 is what? Degree of freedom. So order of k is what? Degree of freedom times degree of freedom. Then we have what? Displacement matrix. Okay, and what is the order of displacement matrix? 2 cross 1. 2 is the degree of freedom. Okay, so it is degree of freedom times 1. Okay, so let me take another example here. Let us say we have a bar here. Okay, it have two elements. Okay, now let us say we have number of nodes here is 1, 2 and 3. Okay, now let us say a force F is acting here. Okay, now that what will be the total number of nodes? Degree of freedom is what? Total nodes, right, times degree of freedom of each node, right, each node. So from here what is going to happen? Total nodes is 1, 2 and 3. It is going to be 3 times in, you know, in bars, in a bar 1D element with axial force, there is only 1 degree of freedom, right, because of force F, they can only, you know, elongate, right. So the displacement of node is only in along one axis. Okay, for example, if it is x-axis, so the 3 node can only displace like this, right. It is 3 here, maybe it can be like here. Okay, so 2 is here, maybe it can go here. So only in along one axis there is degree of freedom, so total degree of freedom of each node is only 1. Okay, so it is only 1, so 3 times 1 is 3. Now when you write the force, you know, the stiffness equation, F matrix is equal to K times U, right. So the order of F force or load matrix or load vector is going to be what? Total degree of freedom is 3, right. So it is going to be 3 cross 1, and here it is degree of freedom times degree of freedom, so the order of stiffness matrix is going to be 3 cross 3. And for the, you know, the deformation matrix, okay, or the deflection matrix, the order is what? Degree of freedom times 1, so it is going to be 3 cross 1. Okay, so in short, if we have n degree of freedom, the order is going to be n cross 1, and for stiffness matrix it is going to be n cross n, and for the displacement matrix it is going to be n cross 1. So n cross 1 and n cross 1 common for force and the displacement, and for the stiffness equation the order is degree of freedom times degree of freedom. Okay, so I hope you understand everything. If you have any doubts, you can comment or you can contact me. Okay, so in the coming classes we will solve more problems on the, okay, on these 1D bars. Okay, so that's it for today. See you in the next class. Thank you.